Welcome to Lab 3 Circuits. So what is the purpose? The purpose of this lab is that we basically want to observe the behavior of circuits with resistors in series and in parallel. We use a multimeter to measure the conventional current and potential current difference of the circuits, and then we want to predict the behavior of the circuit and examine the behavior of the ohmic resistors and capacitors. So our results, in the series analysis, we found a potential difference of negative 0.93 volts across the 47 ohm resistor and negative 1.996 volts across the 100 ohm resistor. And the total algebraic sum was approximately 0.024 volts. So in the RC circuit, we discovered that it takes 10 seconds to charge and 12 seconds to discharge, as well as in the 20 ohm RC circuit, we discovered that it takes 18 seconds to charge and 21 seconds to discharge. So fundamental principles. So we use Kirchhoff's current law, which basically states that the total current entering a junction equals the total current leaving it. And then we also used Kirchhoff's voltage law. So the sum of all voltages gained and dropped across any closed loop in the circuit is zero. And then we use Ohm's law. The current through a conductor is directly proportional to the voltage and inversely proportional to the resistance. The relationship. We also use the relationship between electric field and potential. So the field points in the direction where the electrical potential decreases most rapidly, with a strong field causing a faster potential. So capacity and store charge, we also use. So the ability of a capacitor to store electrical energy with stored charge equal to capacitancy multiplied by applied voltage. So in our series overview, so the system was the circuit. We had two batteries, both were 1.5 volts, so a combined total of 3 volts. We have two resistors. One would be the 47 ohm resistor, and the other one would be the 100 ohm resistor. And then we had two amp meters. As you can see in our diagram below, this was the diagram we were given. And over here is our results. So we found that the combined 3 volts, we get that I1, or the amp meter on the top, and I2, they should be equal to each other. So they should be about 0.2204 amps, or 28.4 milliamps each, which makes sense. And then checking around, I have I have a list of all the points where it actually is not equal to zero, and the chemical cell. So as you can tell, at each point in here, there's zero at certain points, and then you sum them all together. So you'll end up finding that the ideal wire is, or the wires altogether, the voltage is equal to zero, which makes sense. Here's a graph of our data around the circuit. So these are the voltage measures around our circuit. So you can tell around this area right here, around F, it all goes to zero, but the sum of all this combined should equal zero. So our experimental calculations and observations in our parallel circuit. So the current shift, loop current increases significantly from 0.2 amps to 0.6 amps. The mechanism, an ideal ammeter, features near zero resistance. Placing it in parallel bypass short circuit. The 100 ohm resistor causes the current to completely avoid the path and reduce total current resistance down to just 47 ohm resistor. So these are our calculations over here. And then RC circuit. So the overview of our RC circuit, we had one F capacitor, we had a 10 ohm volt, a 20 ohm volt, and then two 1.5 volt batteries. What did we observe? So we observed that in a perfect simulation like this, it should take the same amount to charge as it takes for it to discharge. So it took 10 seconds to charge the ohm volt, or the 10 ohm volt. So it should take 10 seconds to discharge. It should take 20 seconds to charge the 20 ohm volt, and its discharge should equal. So it should take 20 seconds. Again, the disclosure is, since it's a perfect simulation, it will work as a perfect circuit, so we won't lose anything to heat or anything. So if we use 5t, which is the amount of time, these are the results we should get. So as you can tell down here, ohm times 0.2 F equals 2 seconds. Here's a graph of our data. So this just, so I have a slide. So the left graph, the panel tracks the actual voltage drop you would read on the voltmeter as time increases. So resistance dictates speed. The 10 ohm volt curve drops much more steeply than the 20 ohm volt curve does, because the 10 ohm volt offers less resistance, which allows current to flow out of the capacitor faster. What is the meaning of tau? So at t equals 2 seconds, 1 or tau equals 2 seconds time. One time constant for 10 tau. Notice that its voltage has dropped from 9 volts down to about 3.3. So this is exactly about 36.8 of its starting value. And then what does the right graph tell us? So that panel tells us the natural log of the data. So the change in our volt over the change in our voltage at the start, and then turning the exponential curves into straight lines. So we take this, we find the slope of this, and then that represents how many seconds it should take to discharge. So yeah. And then sources of error and discussion. So the simulation was pretty much a perfect circuit. So again, we didn't lose anything. Our circuit should be working perfectly. If there was any issues with our data, it was more than likely operator issue.